This is a session on CT dose, and it's and on getting the and then once you achieve a certain dose, what can you do best to make sure you get the best images possible using that dose? And that's going to be Frank's talk. I'm going to give you some, just basically review some of the basics of CT dose. And I think I'll get started right now. My name is Donovan Bakalyar. I'm from Henry Ford Hospital, and welcome. The radiation delivered by a CT scanner is determined using a variety of parameters under the control of the operator. The multiplicity of terms used to describe these parameters can add confusion to what should be essentially a very simple task: characterizing CT radiation output in terms of the dose delivered to a cylinder. Now, it may not always be a good idea to investigate radiation dose clinically. So perhaps we should try to learn what we can from phantoms. Now, here is our first attempt. Now, even though this phantom seems to be unharmed, as far as we can tell by the low level of radiation used in CT, it's far too transparent, and it also doesn't hold still very well. So rather than use phantoms, we decided to go with a chunk of plastic. For the time being, we're going to confine our discussion to a cylinder of infinite length. And in order to keep things as simple as possible, we start, as in the TG Task Group 111 report, with an infinite scan of an infinitely long cylinder. During such a scan, the dose at any point in the cylinder will asymptotically build up to its ultimate value, DEQ. The spatial average of this value, DEQ bar, can serve as an indicator of the scanner output, and along with the total number of rotations n, determine the total energy, which sometimes E sub tot, absorbed by the cylinder. If a finite cylinder is long enough, a scan through it from one end to the other will yield these values in its central plane. So, topics to be discussed: operator-controlled factors going into CT radiation dose, the infinite cylinder as parameters in TG 111, details in the development of DEQ and its relatives, the finite scan, the rise to equilibrium called H of L, that's a function, and CTDI and its relationship to some of these other parameters. They're very closely related. And the size-specific dose estimate and accounting for patient size. CT dose. The radiation dose from CT is relatively high, often in the same ballpark as interventional radiology and cardiology. In many cases, that's come way down. There is some difference in that ordinarily the radiation in CT exams is applied more uniformly, and so there may be less risk of radiation burns than for interventional procedures involving the same total absorbed energy but focused in a smaller region. There have been some exceptions, but those have generally been mistakes. So what is it that determines how much radiation the point on this patient right here will absorb? Here, X is chosen to be a point on the axis of rotation. For this discussion, consider the tube potential to be fixed. Also note that because the symmetry of the model, we can ignore the effects of gantry rotation. One implication of that is that there is actually there's some discussion going on as to whether or not it means anything to list a CTDIVOL for the scout view. In a certain sense, there is. because really it doesn't have anything to do with rotation. It certainly wouldn't in a cylinder. So we can increase the current, and that will increase the radiation dose. We can decrease the current, and that will decrease the radiation dose. Or we can control the amount of time the X-ray beam is on. These apply to everything, but they apply in particular to the axial scan, where the table is fixed during the application of rotation. During the application of radiation. We have been looking at one data acquisition cycle of what is officially called an axial scan. Sometimes it's called a sequential scan. That's Siemens terminology. And scan and scan is a term that Toshiba often uses. An alternative method of scanning is called a helical or spiral scan, where the tube is left on and the patient is moved through the beam continuously. Now you can move the patient through the beam slow, for a long exposure time, or fast for a short exposure time. Now, Frank's going to discuss one of the problems of getting too carried away with moving patient through the beam quickly and bragging about how much dose reduction. This is often left to the misconception that it's really good to have a high pitch. Frank's going to go into that to make sure that, and this is a misconception, it's often in the pediatric community, and make sure that that this is understood, that it's actually the reason to go through fast is to go through fast. It's not necessarily to go through to get it to reduce dose. You use a high pitch if you need it to get through in a hurry. We could increase the time the point and the patient was exposed to the beam by widening the z-axis collimation. And that will increase the dose to that point. And points off the axis of rotation may be exposed for more time if they are close to the detector, or less time if they are closer to the tube. If the gantry is rotating, this will even out some. Mass confusion. Though the meaning of MA, milliamps, is clear, S can be ambiguous in CT. I think over the past few years people have been a little bit more careful in saying what they mean by MAS, but one has to be awfully careful when one goes from vendor to vendor. When S means, as shown in the previous slides, the time that a point on the axis is exposed to detected radiation, okay, not the whole beam, but the part of the beam that's used for making images, MA times S is called effective mass. That's a Siemens term, and it's also used by Toshiba, or MAS per slice, Phillips. This has become, effective mass has become the term that's become accepted in the community. Thus, effective MAS, or MAS per slice in CT, has essentially the same meaning as MAS does in other X-ray applications. It has to do with the amount of time a particular point is exposed to radiation times the tube current. It's not really a word, it's more of a mix of an acronym and an algebraic symbolism. And when used by itself in CT, MAS often, but not always, means the MA times the time per rotation, which is not the same thing and does not tell as complete a story as effective mass. If you had to have one number, effective mass is a better one to use. GE doesn't use it, but you can always calculate it yourself. It's now sort of semi-official in the AAPM CT lexicon. Rather than using MAS and calling it a word rather than a symbol, it's officially called the tube current time product, and effective mass is called the effective tube current time product. There's actually a value to this, to calling it this. It's sometimes it's like when you ask somebody how much they weigh, you ask somebody how many pounds they are. It's not always clear that you're distinguishing between one or the other when you use the same word to describe both. So having this down here is of some value. I don't know how popular it is yet. Now, one thing that's a little bit subtle, but most of you are all aware of this, is that the width of a detected beam versus is wider, is a little bit less than the actual beam width. And this makes perfect sense. If you tried to collimate the beam to exactly fit the detectors, there's got to be some vibration in these beautifully engineered machines. Despite no matter what you're doing, when you're whirling something around and you've got 28 G's of force of acceleration acting on all of the hardware in the gantry as it's rotating, there's got to be you've got to have a little bit of slop in your system so that if there's a little bit of vibration of the beam relative to the detectors, that you're not clipping the edge of the end detectors. And so the geometric projection of the z-axis collimation onto the axis of rotation by a point focal spot has been referred to in the literature. Dixon and Boone have talked about this, and Dixon has talked about this a lot. Generally, the symbol used in their papers and in the TG 111 is just the letter A. For MDCT, A is greater than NT to keep the overbeaming penumbra beyond the active detector detector length NT. This is also called overbeaming. So, which one is correct, A or NT? Now, this isn't a SAM session, so we can't ask it with the little things that you click on. But for a show of hands, how many think A is correct? Nobody. How many thinks NT? How many think NT is correct? Which one is? Yeah, that's the answer. Correct for what? In some of our dose literature, we've been in pointing this out. We sometimes imply that because we're concerned about dose, that we should just be concerned about the actual beam width A. And for dose considerations, that's true. But for noise considerations and for signal considerations, it's really NT that matters. So the two are often very close together. When you have a reasonably wide beam, there's a few percent difference between them. But when you get to a very narrow beam collimation, which you might use for specific purposes, such as wanting to get a really high quality image, you could have a beam width that's substantially higher, almost double that of the detected beam width. And this you can think of this as that you need a certain fixed amount, not fraction, fixed amount of beam overlap to make sure that there's no problem with the edge of the beam clipping the edge of the detector. So this is dealt with by some of the manufacturers. I don't want to leave anybody out, but I know GE has a term when if you were the technologist setting things up. I know GE has a term called efficiency, and this is what they're referring to. You will know that the efficiency is usually 90-something%. But if you go down to a narrow beam width, you'll see that the efficiency will go down to 50-ish%. So they list that as information to the technologist to note that, look, you're going to get the same amount of photons that you're making an image out of, you're going to need twice as many as you do if you were using a wider collimation. Philips has a warning. When you go down to a narrow beam width, they'll pop up with a warning. Look, your dose is going to be higher than you might think. So this is the way the manufacturers deal with it. But both are correct depending on what you're doing. Most of the definitions in CTDI are based on NT, not the beam width A. Pitch. Pitch is just a table movement per rotation divided by the detected beam width. So I'm using B as the table increment per rotation, as a symbol for table increment per rotation, and I think I've been consistent throughout my slides. I apologize if I haven't. And NT is, of course, the part of the beam measured at the axis of rotation. That is the part of the beam that's used in making images, the detected part of the beam. Okay, so as the pitch gets higher, it's like a screw thread that rapidly goes through the has a high pitch. I mean, I'm using. So it's in CT. It's a lot like, also sort of like somewhat related to a duty factor. The smaller the pitch, the more the overlap of the beams, the higher the pitch. You might even avoid overlap altogether if you have a pitch greater than 1. This is sort of how it works. Here the pitch is 1, here the pitch is 2, and here we have a multi-slice CT, and here the pitch is 1, and here the pitch is 2. Interestingly, if you looked at the actual mathematical shape of the helix with the pitch 2 here, it's the same as the pitch equal to, it's the other way around. Pitch 2 here looks like the pitch 1 here in terms of the shape of the helix. Now, this is pretty much universally the definition of pitch. However, there's a legacy, and out there, some of the early on Siemens used with their first multi-slice, they used the definition that instead of dividing by the beam width, you divide by the slice width, so you get bigger numbers. Toshiba today still uses both. They call one the helical pitch, and the other one the pitch factor. The pitch factor is what we normally call pitch. And the helical pitch, so often you'll get a helical pitch of like 20, 30, or 50, meaning that it's the table movement per slice. So it can be a very high number. Again, Toshiba uses both, and they distinguish between the two. Pitch and effective MAS. I'm not going to dwell too much on this because the equations are going to be available in the slides that are available, and I hope to send out a little bit of a corrected version. I haven't changed them much, but changed them a little bit. Anyway, what I said was that pitch and effective MAS. This is the equation that's usually used to define effective MAS, but what I told you is that it's the tube current times the amount of time that point is irradiated. And let's just go through a bit of a proof, starting with this is the tube current times the time that that point spent in the beam as it was passing through the beam in a helical case. And that time is just nt divided by the velocity of the table. And we go on to the next slide, we do a little algebra, and it comes out to be ma times the rotation time divided by the pitch. Interestingly enough, what I told you earlier, well, maybe it's not that interesting, but I'll explain it anyway. What I told you earlier is that the effective mass was independent of rotation time. It still is, and this comes up a lot. You've got rotation time in the numerator, but buried in the denominator in pitch is also the rotation time. But if you go back to a little bit more fundamental equation, it's really not dependent upon rotation time at all. The effective mass is not. But both this and this end up canceling out if you take pitch and beat it up a little bit and expand it. You'll end up being able to cancel rotation time. But the way we think about it usually is this way. Okay, now our dose profile. Because of scatter, the dose profile can extend well beyond the nominal collimated beam width A, and in those profiles more or less independent of the beam width. It's not a fraction of the beam width. It has, because it's so large in comparison to most beam widths. It doesn't change much as you change beam width, and this has ramifications in the way we deal with it. This is actually based on some measurements. Now, let's consider a sequential series of axial scans on a very long cylinder. So this is supposed to be time going down. So this is the first exposure. Then the table will move, and we'll get a second exposure, and so forth and so on. The dose received by this particular point, delta V, it will be the sum of the doses that it gets as it passes through the gantry. If we are sampling along the cylindrical axis here, if we're the axis of symmetry, and if the cylinder is symmetric with the axis of symmetry, In a helical scan, the dose that this sees will be the exact profile, including scatter of the dose profile. If this is off-axis, when you go through, it'll be modulated due to the thickness of the cylinder itself. Anyway, so let's see how this works. In scanning a long cylinder, the gantry's over here. Okay, the CT machine will make an exposure. The point here is going to pick up a tiny bit of radiation from the tail, and we're going to register the result that we get here on it will amount to be a graph of the cumulative dose as a function of time. So this has received a tiny, insignificant dose from this particular exposure. But as it goes through, it's going to pick up, it's going to continue to get a little bit until it starts getting into the body of the, where there's more radiation. And it'll continue to pick up more and more and more. And then as it passes through the beam, it'll continue to grow, but asymptotically approach a point up here, which we call DEQ in TG111 report, and that amounts to the limiting dose that this thing receives. And it could go on and on forever and it wouldn't grow at all. Now, notice here that the cumulative dose that this thing picks up is substantially larger than it would have received had it just been sitting in the middle of the beam. It's all of this scatter adds a considerable amount of dose to the patient. It's not good for anything either. The scatter isn't good for anything either. Also, if you can imagine, if we had a higher pitch in a cylindrical CT, or if we had the equivalent of just moving the table more between scans, which we usually don't, we usually try to make in axial scans the beam width and the table movement equal, you could see that this would go down. But if we bunched these closer together, it would pick up, if we had twice as many points along here, this would probably grow to be about twice as large. Okay, so this is the dependency upon the pitch is sort of implied here. So the dose from the scan, this is just equations. We can actually look at it and compare it to an integral. This is really a dose acquired in this way is like a numerical integration of a function. Okay, and so this would be a really expensive integrator. Is the accumulated dose. So approximately this DEQ is related to the integral of the dose profile divided by the table movement per rotation B. Because it's done in jumps in our axial scan, it's a sum, but they're pretty darn close. Now, alternatively, we could have gotten the same information by having a bunch of dose detectors all the way along the cylinder, taken one, just performing one exposure with the table fixed, measuring all of these and adding them all up. We would have gotten the same result. So this is the basis of CTDI. It's an equivalent way of acquiring the same information. Again, to get the same number that we had in the previous slide, these detectors would have to be the same distance apart as the table movement per rotation. But this is a beautiful thing. We can get all of our information in one shot. This used to be a big deal back in the days when gantry rotation was cumbersome, and you had cables that got twisted up, and then you had to untwist them and so forth. But today's modern scanner, you could have just done what we did in a couple of slides ago and just actually scan the phantom rather than using this alternative method which gets you the same information from a single scan. Get over there. Okay, so infinity is kind of impractical, so how long does a cylinder need to be to effectively reach DEQ? It's convenient to define LEQ as the value of L where D has reached 98% of its limiting value. It's an asymptote, so you've got to define it somewhere, and this is where it's been defined. This is around 45 centimeters for a 32 centimeter diameter acrylic. And so this means we have we'd have to put at least 3 cylinders, 3 CTDI cylinders together end to end to get the full impact of the dose profile. Now, if we were to do that, only the central slice receives this high dose. The dose, if we scan in this way, we don't. So now DEQ refers to, if we scan this finite amount, only to the dose received at the central in the central slice of the cylinder, not the ones near the ends of the cylinder. Also notice in an infinite scan, I don't know why I put this in here, because, yeah, but this last sentence, no, that's correct. That's all right. Okay, so TG 111 suggested that we use a longer phantom, and the TG 200 phantom, as built by John Boone and his team at UC Davis, is such a cylinder. It's 30 centimeters in diameter, 60 centimeters long, and is made of high-density polyethylene, which is relatively easy to get and not too expensive. It's a little lighter in weight, but this is heavy. Each one of these weighs about 30 pounds, which is roughly the weight of the single CTDI phantom. Some of you have been worried about hauling this around from place to place, but the TG200 intent is hopefully to get these measured in one place and make measurements that authenticate or verify the measurements made in a longer phantom. So we're working on that now. Now DEQ bar is just the average dose over the central portion, over the central plane. Or in an infinite plane, actually if you really did an infinite scan on an infinite scan on an infinitely long cylinder, you would get a different dose in the center than you did at the edge, but DEQ would actually represent the average in that particular case. Now for the shorter scans that we use, DEQ only applies to the central plane, and DEQ bar only applies to the central plane. This is very much like CTDIVOL. Now here's an equation. It's kind of a nice equation that's in TG 111. I think there's a little mistake in TG 111 too. Careful if you actually want to go through this. It's not hard. It just takes the total energy and demonstrates that it's the total energy absorbed by this infinite cylinder has nothing to do, of course it's an infinite cylinder. It doesn't matter whether it's uniform or not. It doesn't matter whether the scans are all in one place or whether they're, because we're only counting the energy. We're not talking about the energy density. We're not talking about the dose. So it's just simply the energy absorbed in one scan times the number of scans, regardless of where they are. What this amounts to is if you do this uniformly and so forth, is that you can easily show this is equal to the length of the scan if you were to do this in a helical fashion or an axial fashion times DEQ bar. Notice how this looks an awful lot like DLP. In fact, this sort of justifies DLP to some extent. DLP still has a lot of issues, but this sort of puts it in a proper framework. So one important note that is that even though this here is the volume, right, of the scanned section, and DEQ bar is the average value in the central plane of this scan, DEQ bar, the energy is not totally contained within this. It still spills out. If you do a finite scan, it still spills out over the edges. So this is not the average energy within the cylinder. It's a way, this is another way of stating what the total energy is. It's a subtle point. Finite scans on an infinite cylinder. Now consider a scan of length L along a line in the z direction within the cylinder. The dose at the center of the scan is going to be a function of the scan length. We're not doing an infinite scan anymore. If we take this limit and go to, if we take the limit as we go to infinity, this d as a function of L will go to dEq. Another way of saying d of dEq is just saying d of infinity here. If we define a function h of L, and we call it the rise to equilibrium curve, if we define this as del over dEq, it's of course normalized. It becomes, this number becomes 1 for an infinite scan, and it goes all the way to 0 for a scan of 0 length. Now, what's interesting about this is experimentally, this curve is nearly independent of kV. This scatter component is significantly greater in the center than at the periphery, so this function is also a function of radius, okay, of the distance from the center. But it's practically independent of kV. It's almost independent of collimation width. And it seems to be fairly independent of scanner, which scanner you use. So it's not a completely constant function, but it's pretty darn close. And this makes this very, very useful. Now, what's the difference between CTDI and D? CTDI divides by NT. So this is the dose divided by NT of the integral over a finite length of the dose profile. D is the same thing, except it divides by the table movement per increment B. So this is actually the dose in this plane. This is not quite the dose, because this has to do with the detected beam width, not the total, or not. This is not the beam width per. Excuse me. It could be okay if NT was equal to B, which it sometimes is. Yes, often is. That would be a pitch of 1. Okay, so then if for a pitch of 1, this and this are the same. Now, if everything goes to really, really long lengths, that is, if L goes to infinity, this becomes dEq, as we stated before, and this becomes CTDI sub infinity. We usually don't use CTDI sub infinity. We usually use CTDI sub 100, which goes to plus and minus 50 centimeters here. So it's a finite part of this. Now, how does a finite scan look? Well, if we take a finite scan and we use only part of the dose profile, it's as if we exposed here, here, and here in that long series I showed you earlier. We don't get the dose. Oops. We don't get the dose in the tails. We leave a little bit off. It's still a significant fraction, say something like, I'm going to throw out a number like 70% of the total. It's not the complete total. But CTDI 100, for example, does not capture the same amount of information that you would get from CTDI. Well, it doesn't reach the value that we'd get for an infinite scan. There's nothing really wrong with that. It just doesn't. So it's a little more complex here. This is actually, I actually drawn this so that you can see this is the final value that you get from these 3 scans. And it is not equal to what you would get for an infinite scan. That's not rocket science. It's pretty obvious. Now, if you capture the dose profile by using a particular kind of ion chamber that has a dose rate that plots the dose rate as a function of time, and you convert that dose rate to a distance, you can integrate this over a short length for what would be the equivalent of scanning a short distance. A longer length yet, a longer length yet. Oh, and I put this word added here because I threw this slide in. It's not on your if you printed it out. And here's a longer length, and here's a longer length yet. Now, what this is if you plot the integral as a function of length, of course, if I make the length 0, I'm not going to capture anything. If I make the length infinitely long, I'm going to capture the entire dose profile, and in between it's going to rise in a very, very smooth and predictable fashion. This is called the rise to equilibrium curve, and this is the terminology that's now in the literature and in the task group reports. This slide is from Sarah McKenney, who is part of the task group. And I want to add one concept here that's very important, and it's been confusing and to people to understand. Well, what do you do for a stationary? Well, if you stop to think about it, if you have a stationary table, and if you have this point, and you irradiate it this way with, say, a cone beam, for example, or you irradiate it this way by continually exposing and moving it through, it really doesn't matter. You're getting the same thing either way. These photons have nothing to do with each other. You treat them as independent. You treat each of these scans as independent. The total amount of dose received here is going to be about the same as here. There are cone beam effects and so forth, and there are details. What that also means is that CTDI, you get a number CTDI when you do a stationary table scan like interventional. The idea that well, how do you apply that when CTDI has been sort of invented for a moving table in a scan? But it doesn't matter if the table moves or not. It just matters what the irradiation length is. And of course, if the beam width is shorter than 10 centimeters, which is the beam width used, or the table, the exposure irradiation length used in calculating CTDIVOL and CTDI 100, if the beam width is less than that, then the dose that the patient is getting, or the dose that the phantom is getting in the central plane, is lower than the number for CTDI 100. If the irradiation length is longer than 10 centimeters, the dose is going to be higher. It's going to follow that H of L curve. So there's nothing wrong with getting CTDI 100, but that is not the patient dose. The patient dose is actually lower when you have a fixed table and you're using a beam width that's narrower than 10 centimeters. And you're usually going to be using a couple of centimeters in an interventional procedure. So you have a substantially lower dose being delivered to the highest dose portion of the patient than you might think if you were looking at CTDI 100. Okay, CTDI using a pencil chamber, the dose profile gets clipped and attenuated. The pencil chamber captures part of it here, leaves off this much, but you don't have to move the table, and you can capture what you would get had you gone through a 10 centimeter scan. If you had an infinite phantom, two things happen. If you had an infinite scan and an infinite phantom, two things would happen. You'd pick up a tiny bit more dose because there's a little more scatter in the ends than there is for the shortened CTDI phantom that we usually use. Is 15 centimeters long, but the vast majority of the difference is just due to not taking the complete integral over the whole length, enough to capture the entire dose profile. The effect, I was a little surprised because I actually went out and measured it, and you can get it from the literature. The effect of cutting the phantom off at 15 centimeters doesn't change things much from what you'd get if you tacked on a bunch of additional plastic at the end of each one of this for doing CTDI 100. Okay, so here's another way of looking at how it's done. We're going to water a plant, and we're going to water a plant by squirting it. We're going to turn this sprinkler on and off and move the plant down, and so this is like doing a cylindrical scan, and this is how you would water the plant doing a cylindrical scan, and you can see in the center you're capturing a lot more, and as you tail off the edges, the amount you get per squirt is a little bit less. If you were to do this in a helical fashion, you would just leave the hose on and you would just move it down there. But you could rig it if you did everything right. You'd rig it so you get about the same amount of water in the box. Now, an alternative way of doing it is having this really long tray, doing one squirt, acquiring the same amount of water you did the first time when we were moving the thing through the box, and then just pouring it into the planter. So that's sort of the equivalent of how CTDI 100 works and how things work with the long chamber. Now, something to look at here is what if we don't do a complete scan and capture all the water out of the edges, and we limit ourselves to a finite length. We don't get quite as much water as we get. We miss some of what we would get had we done an infinite scan. Okay. So we have three situations. We've got this tray that's long enough to capture the entire amount of water. We've got this tray that's long enough to capture the entire amount of water, and we've got this tray that's a little bit shorter, and this is like our CTDI 100 chamber, or the 100 millimeter chamber that most of us are used to using who make these kinds of measurements. Now, both of these will capture all of the water, but you'll get a different number when you read your dosimeter with this chamber than you will with this chamber, is if you're reading dose or if you're reading exposure. That sort of corresponds to the height of this. But that's why when you look at the CTDI 100 or CTDI 100 equation, the length of the chamber comes into play here. I don't have time to go into that any further, but that's the reason the length of the chamber is in the equation. So, what is the weighted average? The weighted average is when we take CTDIVOL and we take that equal to 2/3 CTDI 100 measured at the edge and 1/3 CTDI 100 measured at the center. This turns out to be a reasonably good approximation of what you would get as an average over the whole area. Note that we divide by P. We divide by the pitch. Now what that does is makes CTDIVOL look a lot more like the D function I was showing you earlier than the CTDI function I showed you earlier. One of the things that's kind of interesting about this is that NT is in the denominator here, and it's in the numerator over here, and so it goes away. Now, those of us who've been making these have been doing ACR accreditation for a while, notice that there was pages and pages published on what we really mean by NT, because that was a source of real confusion. But when you calculate CTDIVOL, it doesn't matter. You could put in any number you want. You could put in negative square root of pi. It doesn't matter. You can go to your dose tables and your Excel sheets that you get from the ACR. You can put any number you want in for N or T, and CTDIVOL won't change because it's in the numerator and in the denominator of the ultimate equation. A lot of other numbers were changed, but not that. So CTDIVOL is not dependent upon NT at all. It's factored out of the equation. Now, CTDIVOL is a useful index of scanner output. This is a very nice paper done by Turner et al. At UCLA, where they took a bunch of different scanners and did Monte Carlo calculations on different organ doses as a function of which scanner you used, but normalized to CTDIVOL. And you can see that, yeah, there's a little bit of variation, different organs, but by and large, it doesn't matter which scanner you use. You get the same organ doses regardless of the scanner, as long as you normalize to CTDIVOL. What that means is CTDIVOL is a very good indicator of machine output. It's not a good indicator of patient dose. It's a good indicator of dose to a specific cylinder, using the techniques that you're using on that scanner. Where I find this to be useful is when you buy a different scanner, a different brand. What we used to do in the past is try to set everything up, and then we would, make the tube currents the same, and the images would look quite a bit different from each other. But that's only because some scanners require a lot more tube current for the same output as others. A lot of reasons for this: tube angle, the design of the tube, and also the design of the bow tie filter. Both have to do with this. So, but the CTDIVOL takes care of that because it's a measurement. It's a measurement made. So it's a measurement made inside this piece of plastic. And so it effectively gets rid of all of the effects of the nuances and idiosyncrasies of the design of the scanner. If you set your things up initially by normalizing the CTDIVOL, that's not a bad way to go. Patient size. Well, CTDI 100 we traditionally measure in the center and the edge. for two sizes, and sometimes we measure for error. If you measure at the center and the edge, here the center value is always lower than the edge value. Well, it's not always lower than the edge value. It is in these situations. For our larger phantom, notice they differ by roughly a factor of 2, and this is what all of you have seen, at least at 120 kV, and it doesn't vary all that much as you change kV. They're much closer together for the smaller phantom, and if you measure an error, which you could think of as an infinitesimally thick phantom, of course they converge because the center and the edge are at the same place. Now with more data, it turns out it's interesting. You get kind of a peak here. This is from a paper by John Boone and his student, and these are all infinitely long phantoms. For an infinite scan, you get this bump at a certain radius of phantom. This distance, the x-axis here, is the radius, is the diameter of the phantom. Okay, and this is the center. I believe this is the central measurement of the dose. And these are all. This is from infinite scans. You get a bump. For a 100 millimeter scan, which is what we use for CTDIVOL, you get another bump. You get a maximum in this curve. And for a very short scan, you don't get a peak, it just drops off. Now, why is this? Well, there's a trade-off between the buildup of scatter and the attenuation. And for small enough phantoms, these play off against each other. Now, this is in effect at a very small diameter. 5 centimeter diameter there aren't people that you're going to be scanning that are that big. So this is more of an academic thing to talk about. But even for an infinite scan, it's only a diameter of maybe 6 or 7 centimeters where this peak occurs. But nonetheless, what this tells you is that the irradiation is fairly uniform within small patients, because even though there's some attenuation as you go toward the center, there's more attenuation, but as you go toward the center, there's more buildup. And those trade off against each other. And what we've seen in some of our different phantoms is that the peak dose does not occur at the center, nor does it occur at the very edge. It may occur somewhere a little bit away from the edge. TG204 did this for a variety of things and came up with a curve that provides us with something that we call size-specific dose estimate, SSDE. And what this does is tells us not patient dose, but this tells us what we would get to a plastic cylinder or to some phantom that was appropriately sized for the patient that we're dealing with. So it's a very nice number to know. It's still a simple number. It's not a detailed computation, and the tables are very useful inside of this. This turns out to be a really good way to think about what's going on with patient dose. Now, next question: is a child the same as a small adult? This gets into pediatrics and the application of this. Is a child the same as a small adult? Well, and I think I'm talking too long. The answer is, what do you think? Which is the child and which is the adult? How many think the child is on the left? How many think the child is on the right? The child is on the left. Okay. Child's 8 years old on the left, and the adult is 8 years old on the right. The adult on the right is 36 years old. I'm sorry. What needs to happen here is the dose received. In order to get the same quality of the image, the dose at the detector. Only this part of the detector has to receive as much radiation as this part of the detector does for the large phantom. So the dose received by the detector has to be higher for a child than it does for an adult. That's an important point. People sometimes wonder why is my noise index screwing me up? You know, I need a lower noise index in a child, and people feel, well, then you're overdosing the child. But we've got the benefit of having far less attenuation for the child than the adult. So that doesn't mean the dose to the child is more than the adult. It means the dose to the detector is higher than it needs to be than it is for the adult. And how does this affect patient dose in a child? It kind of balances out. So one way of dealing with this, that is a very, very crude way of dealing with it, is to simply say, okay, I do my SSDE calculation for the adult protocol that I like, and I include the SSDE calculation to figure out what the dose would be for this child by measuring, let's say, the width of the child, just with calipers or using the Scout view or some such thing. If I make those equal, I'm not too bad. And Goski and Strauss have taken this and done a little bit more to say, well, you should go a little bit beyond that. For a small child, you should be about half of that. And for a large adult, you maybe should be a little bit less of that. But this gives us a sort of a tool for setting up pediatric protocols. It's a different way of thinking about it. It's not the dose that varies. The dose to the CTDI phantom should vary a lot, but the dose to the actual patient may not have to vary all of that much. But you would like to cut it down some. Another very important point is that when we look at children, and this is what we had a lovely talk by Kim Applegate, a radiologist, earlier in the week, who pointed out that in children you're often looking at larger things. Even though the child itself is smaller, which would make you think you had to concentrate everything down, you can tolerate a much noisier image in children. And the other thing she pointed out is pediatric radiologists generally can tolerate noise more, and it's legitimate for them to tolerate noise more because you're looking at different things. I think I'm going to stop there because I think I'm not leaving Frank enough time. So anyway, thank you very much. Maybe I could take one or two questions, if there are any.